Hello, ladies and gentlemen. I'm happy to be here with you to share our work intituled Cross-Regional Transferability of AI Cross-Type Mapping, Insights and Challenge. I'm Valinho Antonio, PhD student at the African Center of Excellence in Internet of Things. This is our presentation outline. According to the Food and Agriculture Organization, we will need to produce about 6% more food to feed 11 billion people that are expected to reach by 2050. And this demand for food in the context of sub-Saharan Africa is expected to triple, requiring an additional 140 million hectares of land for agriculture. So in order to decrease the pressure related to agriculture expansion and somehow that leads to climate change, and inversely, the climate change can impact on agriculture, mainly the production loss, we have to increase the productivity of the most consumed crops, such as maize and sorghum, using a sustainable agricultural manners. And one way for that is to know where crops are growing and in which conditions in order to provide targeted interventions. And one of the challenges that we are facing nowadays in sub-Saharan Africa is that most of our governments collect the agriculture information using a ground-based surveys. However, this method is time-consuming, is expensive to conduct, and it has limited spatial and temporal coverage. And in some parts of this region, is impossible to conduct due to logistical or political reasons. And the use of Earth observation satellite images and machine learning is a viable alternative as it enables to generate cost-effective crop type maps which can be used to know where crops are growing and in which condition those crops are across large areas and in the repeated manner. We can use the crop type maps in order to optimize resource allocation, such as providing extension service to the farmers who really need, estimate production, access food insecurity, and we can use as well the crop type maps in order to assess the impact of some programs or policies designed to improve the productivity of some crops. Therefore, our objective was to evaluate the feasibility of transferring three most commonly used machine learning methods, namely multi-layer perceptron, random forest, and support vector machine, between two different locations and here using only spectral information. We started from the principle that the phenological and the growing patterns of the same crops are more similar than that of different crops, even between different regions of the world. In our study, we focused in two regions, Baraweli, which is located in Mali, and Karamoja, which is located in the northern part of Uganda. We chose these two regions due to data availability, similarities in climate, which leads to almost the same growing season for most of the crops, such as maize and sorghum. For the ground reference dataset, we use the 2019 Mali crop type collected by NASA Harvey's team in 2019, while for the Karamoja region, we used the Uganda crop classification produced by Dalbert Data Insights. These two datasets were retrieved from SAS Cooperative. Additionally, we used the PlanetScope-based maps in order to add land use classes, namely trees, built-up, bare soil, and water. We used Sentinel-2 image to extract spectral response for each class with less than 20% of cloud coverage. And then we ended up having 4 images covering the entire growing season that started from May up to September. However, we didn't get image from June due to cloud coverage. For Karamoja, we had to do mosaics in order to cover the entire region and growing season. As you can see here, for the month of the May, we had to aggregate 18 images. Further, we had to resample the red edge, the near infrared 2, and the shortwave infrared bands with 20 meter spatial resolution to 10 meter spatial resolution in order to meet the bands in the visible and the near infrared. After preparing the reference data and the Sentinel-2 image, we extracted 40 pixels per class in each polygon of reference data set with minimum of 2.5 meter between the pixels in order to avoid overlapping. And then we ended up having, in this case for the maize, 640 pixels for Barawell and 1620 pixels for Karamoja. And then after extracting the pixels, we divided them into 70% training, 30% for the validation purpose. Then we computed the spectral indices mostly used in the context of Sub-Saharan Africa for the crop type discrimination. And these are the ones you are seeing here, from the Merz terrestrial chlorophyll index up to enhanced vegetation index. After dividing our data set into training and validation, we applied the multi-layer perceptron, random forest, and support vector machine, and the configurations are these that you are seeing here. For the multi-layer perceptron, we use the lick-rel function for all units, with the exception in the output layer where we use the linear activation in order to minimize the numerical runoff error. And we use it as well, the sparse categorical cross entropy, to compute our loss, the Adam algorithm, in order to train our model. And within the sparse categorical cross entropy, we specify that we are going to use the software max activation function in the output layer. For the two other models, random forest and support vector machine, we only specify the number of trees and the regularization term, in this case for the support vector machine, to be 50 after main attempt. As a result, the performance of the classifiers on local data set overall were very high. with exception to the multi-layer perceptron that had an overall accuracy of 82%, and this can be related to the simplicity of our model. The other interesting result was that all models decreased their accuracies when applied to Uganda dataset. And this is somehow related to the training data set size, which was relatively larger than the Barawell one. Thereby, it might have introduced more variability, making it harder to generalize. Transferring the models from Mali to Uganda using all classes, we noted that the three models performed very poorly because of the difference in Sentinel-2 backscatter values in each class, as depicted in the correlation map of the radiometric indices. In this case, when we see the maze, we are seeing that there's no correlation between the radiometric indices of Uganda and Mali. The same is observed for the sorghum. However, we got some identifications of sorghum pixel by random forest and bare soil by support vector matching. Surprisingly, using only crops, we noted an increase of overall accuracies and F1 scores for all models in detecting sorghum. When we look at the confusion matrices, we realize that the spectral response for maize and sorghum are most related to sorghum between the two regions. Similar performance we got when we transferred the models from Mali to Uganda is observed here as well. The three classifiers had poor performance. As we said before, due to limited sorghum spectral response similarity between Baraweli and Karamoja, we got an improvement on the three models with highest overall accuracy and F1 score achieved by support vector matching. As conclusions, we evaluated the feasibility of transferring three most commonly used supervised methods: random forest, multi-layer perceptron, and support vector matching between Barawell and Karamoja using only spectral informations. That is because we are aware of the limitations that most sub-Saharan African countries are facing to collect reference data in order to have annual crop type maps. And we conclude that the three models demonstrated strong local performance, achieving overall accuracy of 98% in Barawell and an average 90% in Karamoja. Accuracies of the transferred classifiers when using only classes were diminished drastically, and using only the crops, we noted that the performance of the models were improved, partial to the reasonable similarity in the spectral response of sorghum across the two regions in different years. Multi-layer perceptron and random forest could potentially be adapted from northern Uganda to Baraweli and vice versa to specifically identify sorghum, even though with a slight drop in accuracy compared to a local classification. And we are saying that incorporating additional features such as texture, digital elevation model, crop relative height, temperature, and precipitation could further enhance the performance of the transferred models.